Welcome to the Deep Dive, where we unpack complex ideas into clear, digestible insights. Today, we're diving into a question that, honestly, at first glance, feels almost like magic. How can an AI model look at an image and automatically tell us, with pretty impressive accuracy, whether it contains a cat or, a dog? It's such a fundamental capability. Really underpins so much of modern AI. And understanding it, I think, gives us a real grasp of how these systems actually learn. Okay, let's unpack this.
Yeah.
To maybe guide our understanding throughout this deep dive, let's use a central analogy. Imagine like an incredibly diligent student preparing for a really high-stakes exam. The student doesn't just have practice questions. They have this entire question bank. And here's the key part. Every single question comes with its correct answer already provided. It's like having the ultimate study guide,
Yeah.
basically designed to guarantee mastery.
Yeah, that's a fantastic starting point. Because this seemingly magical ability of AI models, classifying images, predicting values, things we see every day, it really isn't magic at all when you get down to it. It's built on a logical, iterative process that becomes remarkably clear once we dissect it a bit. So our mission today really is to make that clarity accessible, help you understand the kind of ingenious simplicity behind this powerful form of AI learning.
Okay, so let's jump right in then. For those of us who follow the AI landscape, we've definitely heard the term supervised learning loads of times. But beyond just having labels attached to data, what fundamentally defines supervised learning? What makes this specific approach so, supervised?
That's a really good question, and it gets to the heart of it. At its core, supervised learning is all about teaching an AI model using labeled data. And what that means is for every piece of input you give, the model could be an image, could be numbers, could be text. You also provide the correct output. The label, the supervision part, that comes from us, the humans. We're effectively acting as the teacher, guiding the model with these explicit answers. The model's job then is to learn the underlying patterns, the relationships within that labeled data, so it can accurately predict the answer for new stuff it hasn't seen before. To give some concrete examples, just like you mentioned, think of an image of an animal. That's the input. And it's precisely paired with the label cat or dog. That's one pair. Or think about a data set of houses. You've got features like square footage, number of bedrooms, location, maybe the age of the house. Those are inputs. And they're meticulously matched with their corresponding accurate sale price. That's the label. So these are the pairs the model sees over and over again. What's fascinating here is it's all about teaching by direct example. Very direct. Just like our diligent student, right? Repeatedly practicing questions where they have both the problem and the correct solution right there. And through all this repetition, the student or, the AI model starts to figure out the intricate rules, the patterns connecting inputs to outputs. The more high quality practice, the better it gets, the deeper the understanding.
I really like that emphasis on the teacher aspect. It really does clarify the supervised part, doesn't it? And it's obviously clear this isn't just about telling cats from dogs, as fun as that is. You probably interact with supervised learning every single day without even realizing it. Can you maybe shed some light on the broad categories of applications where this method really shines? Especially for our audience who might know the basics but want that deeper layer.
Oh, absolutely. Supervised learning, it underpins a huge array of technologies we rely on daily. We can broadly sort of categorize its applications based on the type of problem it's trying to solve. Think of it like different formats in that exam question bank we talked about. Okay, so the first big category, and maybe the most common one we think of with images, is classification problems. Here, the model's goal is basically to assign an input to one of a predefined set of categories. It's choosing from a list, essentially, like a multiple choice question. So for instance, when your email filters a message into your inbox or straight to spam, that's a binary classification problem, 2 choices. Or in medicine, looking at a scan and classifying it as malignant or benign, again, predefined categories. What's really compelling here, I think, is how these models implicitly capture subtle patterns that might even change over time. Think about spam filters again. They have to constantly adapt to new tricks spammers use, right? They don't get reprogrammed line by line. They learn from newly labeled spam examples. So the insight is that even these simple binary choices, like spam or not spam, can handle incredibly complex, dynamic situations.
Right, like trying to hit a moving target almost.
Exactly. And then the second main category is regression problems. Now, in this scenario, the model isn't picking from a discrete set of categories. Instead, it's predicting a continuous numerical value.
Okay. Not multiple choice, more like fill in the blank.
Well, precisely. Like a fill-in-the-blank question where the answer is a number. Predicting housing prices is a classic example. It's not about deciding if a house is expensive or cheap. Those are categories. It's about predicting a specific dollar amount based on all those features we mentioned, square footage, location, etc. Similarly, forecasting stock market fluctuations, predicting sales figures for a product next quarter, or even estimating, say, a patient's recovery time in days. Those are all regression tasks. The model learns to map the inputs onto a numerical spectrum, giving a specific quantifiable prediction. So yeah, in both classification and regression, the AI model is that diligent student just practicing its question bank, learning to give the most accurate answer possible, whether that's picking a category or filling in a specific number.
That distinction is incredibly helpful. Classifications like multiple choice, regression is fill in the blank. Categorizing versus quantifying makes sense. But here's where it gets really interesting for me. How does the model actually do that? How does it go from being, well, initially clueless, maybe just making random guesses, to becoming so accurate at these predictions? What's the actual learning process, the step-by-step that drives this improvement?
Right. Okay. The core learning process itself, while the math behind it can get quite sophisticated, is actually based on a remarkably simple iterative loop. It's all about trial, error, and correction. Think of it as this continuous refinement cycle. It basically starts with the model making an initial prediction, a guess. And because it hasn't learned anything yet, this guess is often pretty random, could be way off.
Sure.
Then comes the crucial step, comparison. The model takes its guess and compares it directly to the correct answer, that label we gave it, the one from the question bank. From this comparison, it calculates something called an error, or a loss, basically a number that quantifies how far off its prediction was.
Okay, so it knows how wrong it was.
Exactly, it gets that feedback. And this is where the cleverness of machine learning really comes in. The model then uses what you called an adjustment formula, most famously a technique called gradient descent. It uses this formula to subtly modify its internal parameters. You can kind of visualize these parameters as millions, sometimes billions, of tiny knobs or settings inside the model. These knobs control how it makes predictions.
Oh, billions.
Oh, yeah. Modern models are huge. And gradient descent isn't just random knob twiddling. It's a mathematically precise method. It figures out which way to adjust all those knobs, just slightly, to reduce the error next time. It's like finding the steepest downhill path on an error landscape to get closer to the right answer. This continuous, informed adjustment slowly but surely nudges the model towards making better predictions, reducing future errors. So, you can imagine our student again, right? They answer a practice question, get it wrong. The teacher, our label, marks it wrong, showing the mistake.
The red pen comes out.
Exactly, the red pen. The student revises their thinking, adjusts their understanding, and tries again on a similar question, slowly correcting their approach. Now, this raises an important question. How does something so complex, like recognizing subtle visual patterns in cat photos or predicting tricky market shifts, how does that boil down to such a seemingly simple try, fail, correct loop?
Yeah, that seems almost too simple.
Well, the answer lies in the sheer scale. These cycles happen millions, even billions of times, across massive data sets. This allows for incredibly tiny, refined adjustments that over time compound into really high accuracy and what seems like a deep, implicit understanding of the data.
It's quite profound when you think about it.
Yeah.
Such sophisticated abilities emerging from this fundamental, yet just massively scaled iterative learning process. It really does make perfect sense when you put it like that. But, of course, nothing's perfect. No method, however powerful it seems, is without its challenges or downsides. So what are some of the key drawbacks or limitations we need to be aware of with supervised learning? What are the real-world implications of these shortcomings?
You're absolutely right. Every approach has its Achilles heel. And supervised learning, despite its power, definitely faces a few significant limitations. These become really critical when you try to apply it in the real world. Probably the most prominent one is the requirement for large, meticulously labeled data sets. Remember how we kept saying it relies on those human-provided correct answers?
Mm-hmm. The question bank with answers.
Exactly. Now, to build truly robust, accurate models, you don't just need some of these labeled examples. You often need millions, sometimes billions of them. And the real cost here isn't just, computing power or storage. It's the immense human effort involved in creating those labels. Just imagine needing people to manually tag every single object in millions of images, or transcribe every second of audio, or gather precise, verified data for every possible situation a model might encounter.
That sounds incredibly laborious.
And expensive. It is. This data labeling process can be incredibly expensive, incredibly time-consuming, and it's also prone to human error or bias. It often creates a significant bottleneck for many ambitious AI projects. Okay, then another major risk, and this is particularly crucial for an informed audience like yours to understand, is overfitting.
Ah, yes, overfitting. Heard that term a lot.
Right. So this happens when the training data or question bank isn't comprehensive or diverse enough. Or sometimes it happens if the model learns the training examples too well, almost like it fixates on them. Instead of genuinely understanding the underlying patterns, the model might essentially just memorize the answers to the specific questions it was trained on.
Ah, okay. Like our student analogy again. The student who just crams by rote, memorizing the answers to the practice test?
Exactly like that. That's the perfect analogy. They might totally ace a test if it uses those exact questions they memorized.
Yeah.
But you put them in front of a new, slightly different, innovative problem that requires applying the principles they were supposed to learn.
And they completely bomb it.
Precisely. They struggle. The model becomes excellent at predicting things it has seen before in training, but it performs very poorly when trying to generalize to unseen new data. This means the model might look fantastic during testing on its training data, giving you great accuracy scores, but then fail miserably when you actually deploy it in the real world, where it encounters novel inputs it wasn't explicitly trained on. So the insight here is crucial. The true test of a supervised model isn't just its accuracy on the data it trained on, but its ability to generalize its performance on completely new scenarios. And often, to combat this, people use clever techniques, things like transfer learning. That's where a model pre-trained on, say, 1 million generic images can adapt really quickly to a very specific task, like identifying rare birds using only maybe a few hundred specific bird pictures. It's a way to leverage prior learning and need less specific labeled data.
That's such a vital distinction, isn't it? The difference between just memorizing answers and truly generalizing the underlying concept. It really underscores how the quality, the quantity, and maybe most importantly, the diversity of that initial training data, that question bank, are just as crucial as the learning algorithm itself. So today, we've really taken a deep dive into supervised learning. We've understood it as this incredibly efficient, sort of quiz-based method for teaching AI models. It's powerful, it's everywhere, but its performance is ultimately completely tethered to the quality and the breadth of the data we feed it. It really is like that student analogy we kept coming back to. We're basically giving the AI student a complete practice exam with all the answers. It makes their learning incredibly focused, very efficient. So what does this all mean for you listening in? It means that the next time you see an AI categorizing your email or predicting a stock trend or, yes, identifying a cat in a photo, you now have a much clearer picture of the meticulous, iterative, and very data-intensive training process that empowered that AI to do what it does.
Exactly. And building on that, the performance of any AI model, much like that student's final exam results, ultimately hinges on just how complete and diverse its question bank was, and of course how diligently it practiced, how much it iterated through that cycle of prediction, error calculation, and adjustment to refine its understanding. It's really a testament to the sheer power of learning from well-structured examples, just done on an absolutely unprecedented scale. Now, next time, we're going to shift gears quite significantly. We'll explore unsupervised learning. That's a truly fascinating area where AI performs its own kind of magic, finding patterns and grouping data all by itself without any labels from us teachers.
Ooh, intriguing. Learning without the answer key.
Pretty much. Prepare for a deep dive into how AI makes sense of unlabeled chaos. That'll be in our next episode, AI, the magic of self-grouping.
Fantastic. Well, thank you so much for tuning into this deep dive today. We really hope our exploration has given you a much more intuitive and maybe a more nuanced grasp of how AI learns through supervision. Remember, AI's learning journey, much like our own, is profoundly shaped by the guidance or lack thereof it receives. Be sure to look out for our next deep dive on unsupervised learning. We'll see you then.